Welcome, students. Today we want to discuss about function of several variables. So before we go there, let's recall what is the function of one variable. So for this whole course until now, we have discussed function of one variable. So f of x is a function of one variable, right? Uh, so you write y equals to f of x. This is a function of one variable. And the idea is if this function is from certain subset of real numbers, right? So let's call it domain of f to range of f, right? This map is also a function from real numbers to real numbers, right? So this is domain of the function, this is a range of function. Here, x denotes the independent variable and y is dependent on x, and hence it's denoted by, and hence it's called a dependent variable. Now note the following. When you want to sketch the graph of this, how do you go about it? You basically draw x-axis for your independent variable, and then you draw your y-axis for your dependent variable, and then you plot it out. Say, for example, if you had f of x equals to x squared, and you want to sketch the graph of this function, you take x equals to 0, you get y equals to 0. When x is 1, y is 1. When x is 2, y is 4. And all the points in between. And then when you draw it smoothly like that, this is how the graph have shapes on. This is how the graph will look like, more or less. Okay, so this is your function f of x equals to x squared. And so we visualize this in xy plane or two-dimensional coordinate system. All right, so as here. Now for function of more than one variable, you will have more than one input. For example, if you can have function of input x and y, let's denote f. So for example, let's take x plus y. So this is a function of how many variables? There are two variables as input. One variable is x, y is another variable. So both of this are independent variable. And if you call this equal to z, then z becomes what? Dependent variable. Okay. So there is no reason why we just can have two, we can have many. So the idea is several real inputs are mapped to single real output number. So this is a function of many variables. So I can similarly have f of x, y, z equals to x squared plus x plus y plus z. So this is a function of, sorry, this is a function of three variables. There are three independent variables. Now, similarly, you can have function of many variables, as many variables as you please. So we'll use a different notation. So there are function of 1, 2, 3. This is the function of n variables. There are n independent variables here. And one dependent variable on it. Okay. So similarly, we can have domain of f where all the inputs, or we'll see what does domain of f means. Domain of f is all those possible values of x1, x2, xn, the n tuple for which the f makes sense. Okay. Now for n equals to 2, we can still visualize it. So the same way you draw the graph for y equals to f of x, in this case, we have two input variables. So let them be x and y plane. I'm trying to draw a three-dimensional perspective. So x and y axis, and on top we have z axis, and suppose I'm looking at x plus y equals to 1. So how will this function look like? So x is 1, y is 1, so you'll be here. So this is 1, 1. And what is the value of z there? So z is f of 1, 1, which is going to be 2. So value of function on top is going to be 1, 2. So it will be somewhere here, okay, on top of this. So if I draw slightly better, somewhere here, okay. What will be the value at x equals to z equals to f of 0, 1 means x is 0, y is 1 is going to be 1. So about 1, the value is 1. Similarly, so these are the output values. Even at x equals to 1, the function is going to be 1. And then basically for every point here, you sketch something on the top here. This is how you can draw function of two variables. We'll give a better way of drawing it in a moment when we talk about level curves. So for the remaining part of the course, we are interested in function of two variables. That means it's a function from R2. So R2 is just a short notation for xy, where x and y belong to R. Yeah. So most of these techniques, actually quite a few techniques will be introduced which will be introduced in this course, can be applied to a larger value of n as well. In fact, what you learned in function of one variable, you'll see how it generalizes to function of two variables and so on. Okay. So there are a few functions drawn here, namely x equals to 1, z equals to x squared plus y squared, and z equals to 3x squared y upon x squared plus y squared. So such things are studied in detail in course on multivariable calculus. At SFU, you have 251 if you're further interested. You can study this in algebra. You can also study this in analysis. Okay. But for us, we'll just do a small introduction and how to use them for business application. So first things first, whenever you're given function, you want to find out domain of the function, right? So let's consider the first function, f of xy equals to 1 minus x squared minus y squared. So to consider the domain of this, so we have to see what are the restrictions for x and y in here, right? There's no restriction really. So here the domain of f is going to be all possible xy, both belong to R. So such a thing is called R2. Okay. Now let's look at the second part. So we have square root of 1 minus x squared minus y squared. Now we know that whatever is inside the square root cannot be negative. That means the inside part has to be greater than equal to 0, right? This has to be greater than equal to 0. So what do we need is 1 minus x squared minus y squared has to be greater than equal to 0. So this means what? 1 is greater than equal to x squared plus y squared. Yeah. Now to visualize this, note that x squared plus y squared equals to 1. is a circle, right? So you have a circle and x square plus y square less than equal to 1 are all the points inside it. So this is your domain of the inside, including the boundary, is your domain of G. Now let's look at the next problem. H of xy is 1 upon square root of 1 minus x square minus y square. In this case, what you need is not only that this has to be greater than equal to 0, but this cannot be 0 either. So if you combine these together, we get 1 minus x square minus y square is greater than 0. We get 1 is greater than x square plus y square. So that means you are inside the circle, but it can't be equal. That means the boundary is taken off. So it's everything inside except the boundary is not there. So I'm going to draw it with dotted line. So this is how you find the domain of a function of two variables. Similar techniques can be extended to function of three variables or n variables. Okay. Now let's see an application to economics. So model X and Y of a certain manufacturer have unit prices and respective weekly demand as QX and QY. So PX will be the demand price for model X and PY be demand price for the price for model Y. QX be the quantity demanded for X, QY be the quantity demanded for Y. And PX is this, PY is this. All right. Of course, the price, these commodities are really jointly related. So you see the price of X also depends on price of quantity demanded for X and also quantity demanded for Y. It will be a nice exercise to basically sketch a graph of this. So let's see. So determine the revenue function. So what is the revenue function of QX, QY? So think about it. So if you have revenue, you're selling two items. So it will be price times revenue of the quantity demanded for the first quantity or the first model X, then price of model Y times quantity demanded of model Y. So this would be the revenue, right? So I will take QX as it is here, multiply by PX, and QY as it is and multiply by PY. And then when you multiply it out and simplify, this is what you get. Now, what is the domain of this function? So what is the domain of R of X? So note that R is what? Is a quantity which the input variables are QX and QY, right? So what is the domain? So we're going to draw the domain. Domain lies in XY plane, or in this case, it will be QX, QY plane, right? So let's draw that QX, QY plane. So this is going to be a QX plane. Then QY axis, QX axis. Note that this is not graph of the function. We are just drawing what? The domain. So now what are the restrictions we have? We need that all of these quantities, even though this is well defined, we need from the real life scenario, we see that QX has to be greater than 0 and QY has to be greater than 0, right? Greater than or equal to 0. So when you solve for it, you get 500 minus QX minus 1 by 3 QY has to be greater than equal to 0, because this is your PX So all these four quantities have to be greater than equal to 0, right? So qx is greater than 0, qy is greater than 0. So if you think about just x and y, qx greater than 0 means you are above the qx axis. Qy greater than 0 means you're on the right of the other axis. Now let's look at the other one. Px greater than 0 would imply 500 minus qx minus 1/3 qx is greater than equal to 0. That means qx is less than what? 1500 minus 3 qx after simplifying, multiplying throughout by 3. And similarly, if you have this greater than 0, py greater than 0, you will get qx is less than qy is less than 15,000 minus 5 by 3 qx. So first we'll draw the lines. Qy equals to 1500 minus 3 qx. So of course I have to scale the axes. So I will scale the axis as 500,000, 1500, and 2000. And then here I will scale it as 100, 200, 300, 400, 500, 100, 200, 300, 400, 500. Okay. So now let's decide how would you draw this. So if you're given a line, you need only 2 points on it. So let's take when qx is 0, I'm taking the first equation here. When qx is 0, your qy is 1500. And when qy is 0, this would give me 1500 minus 3qx is 0. This would give me qx equals to what? 1500 divided by 3, which is 500. So when I draw this line, I will have 1500 0, sorry, 500 0, 0, 500 0. The other one is 1500, and I draw a line like this. And everything to the right is what is my domain. So let me just draw. So for the first part, I mean, it's not complete domain yet, because for the complete domain, all of 4 we should be satisfied. Now, for the second part, we have, similarly, we have 1000 less than 5 by 3 qx. So in that case, when you draw, you have, first you'll draw qy equals to 1000 minus 5 by 3 qx. So first you draw, this is equals to qy. Take qy is 0, then you will get what? You will get 3000 divided by 5, right? Which is what? 1500. So let's work it out. So we get this means what? When qy is 0, you will get what? You will get qx equals to 3000 divided by 5, which is 600. So I'll draw it with a different pen. So we have 600 somewhere here. And similarly, when you have qx equals to 0, you will get qy equals to 1000. So this point here. So what is common to both of them? Since we have less than equal to 0, it's on the other side. And what is common in all of them? This part here. Yeah, so this part inside, which is shaded in yellow, is the domain of your function. Okay. So similarly, you can have more applications. Now matching the functions to their surface. So in this case, let's see one of them. Let's say, let's look at D, for example. So how will the graph of D look like? So we have e to the x equal e to the x times cos y. Now, the way to draw this is you need much more to draw a graph of such a function. But way to draw this is note the following. When x is 0, you will just get what? Cos y. Right? So which one of them have this? When x is 0, it should look like a cosine. So when x is 0, it should look like a cosine wave. So this could be one possibility. This one cannot be. Again here, no, and this one of course not. However, the second thing you should note is that if you keep on increasing x, it will get bigger and bigger and bigger, right? The values will get bigger and bigger, right? So suppose cos is, so y is pi by 2, and sorry, y is 0. So let's say y is 0, and we can keep on increasing e to the x, right? So it will become what? It will become like e to the x when y is 0, right? So we can see that here in this graph, that is being satisfied. So when y is 0, you will get what? You get y is 0, then you're getting something like e to the x behavior. And when x is 0, you get x is 0 is in y line, you get what? You get a cosine wave like that. So the answer is D. Right. Similarly, let's look at A, z equals to sine of xy. Now, when you look at this, note the following, that sine xy value cannot exceed. So sine of xy value cannot exceed 1. And xy equals to 1. So this is how y equals to x graph looks like. So on this graph, the value should be constant. Yeah. So if you notice this one here, in xy, the value here remains the constant. All right. So this is how you can match this function, but the best way would be to discuss the level curves. And okay. So what are level curves? So z equals to f of xy are two-dimensional curves obtained by setting f of xy equals to k. Let me go through it using a simpler example. So z equals to f of xy, which is x squared plus y squared. So what you do is you set z equals to f of xy. So you set this equals to 1. So when z is 1, you get x squared plus y squared equals to 1. So if I draw this, so instead of finding, so there are two ways, right? I mean, like generally you take x and y and then find f of xy. But here in this case, you're taking f of xy equals to 1 or z equals to 1 and finding for what values of x and y you get 1. So in this case, you'll have x squared plus y squared equals to 1, which is a circle of radius 1. So this is your x-axis, this is your y-axis. On x squared plus y squared equals to 1, you get your z is 1. So I will go and draw x squared plus y squared equals to 1 on the graph, right? So, but the level curve will look like this. So level curve is what you go in the xy plane, and what you do is you are finding all values of x and y such that f of xy equals to 1. This will be level curve corresponding to k equals to 1. In this case, we have xy x squared plus y squared equals to 1, which is what? A circle of radius, what? 1. So this will be a circle of radius, 1. Yeah. Similarly, take another one. So another level curve would be f of xy corresponding to f of xy equals to 2. In this case, you're looking for all the points such that x squared plus y squared equals to 2. So that will look like a circle of radius square root of 2. Yeah. So if I want to draw it on the graph, it will look like that. And when you draw all these properly, you will see that this is how the graph looks like. Okay. So if you go at the first example here, this is how x squared plus y squared equals to z looks like. Okay. So that these two examples are done here. Say x squared plus y squared equals to k. For k equals to 1, you will get a level curve like that. K equals to 2, k equals to 3, k equals to 4, k equals to 5. And so you get all these level curves. Note that level curves are basically drawn in the domain, which is the xy plane. All right. So